Okay, so this is activity number 6, and in activity number 6, you're trying to learn and practice equilibrium and LeChatelier's principle. So there's a little bit of a discussion in the beginning in terms of that. Let me show you a worksheet real quick so you guys can see what needs to be filled out. This right here is the worksheet, and in the worksheet, this is similar to what I talked about in this particular case, what I talked about in lecture. Okay, we have a reaction. It's not balanced. Well, it was balanced, but I hit the coefficient. And I tell you what the thermicity is right here. Okay, it's got a negative 135.2 kilocalories of energy. So from that, you know what the whether this reaction is exothermic or endothermic. This is not a balanced equation, but you can see that you have methane and carbon solid plus oxygen goes to formaldehyde, H2CO, okay? In this particular case, what we have here is 4 chemicals, 3 reactant, and 1 product. And then it asks in this table, first, these are the stress on the left. You remove some carbon, you remove some methane, you add some formaldehyde. This particular case is you increase the pressure of oxygen by adding more oxygen. You decrease the volume of the reaction vessel. You decrease the temperature. You add a catalyst, and then you add 2 moles of oxygen and 2 moles of formaldehyde at the same time. So those are the stress that you need to investigate as you determine whether this reaction is going to shift to the right, more products, shift to the left, more reactant, or not change at all, no reaction, no shift in the equilibrium, okay? And again, I want to remind you that what you are doing is you're causing the reactions initially at equilibrium. So everything's at a steady state. Then you cause an imbalance by adding these chemicals or removing these chemicals, or you change the condition. So adding or removing chemicals is not the change that I want. What I'm looking for in your answer is you apply this stress. The reaction is not at equilibrium anymore, but it will go back to equilibrium, or it will try and strive to equilibrium. What happens to the chemical as it tries to make that progression? Okay, the confusing part of a lot of your answers when I'm grading this is that you're thinking that, okay, I'm going to add more oxygen. Okay, I add more moles of oxygen. So you tell me right away that, oh, because I add more than the oxygen increase. That's wrong. And the reason why it's wrong is because you add oxygen, you don't look at that addition of oxygen, you look at an instant after that stress, and you look at the concentration of oxygen or the partial pressure of oxygen as it tries to reach equilibrium again, because adding oxygen upsets the balance. That's not what you're looking at in terms of the change. You're looking at, now that you've upset the balance, what will that oxygen do? Is it going to be decreasing? Is it going to be increasing as it goes back to equilibrium? That's what I want in your answer, okay? I'll give you this one. If you add oxygen, the oxygen will increase, but you will see that oxygen is a reactant. So it's like putting a stress on the reactant side. The reaction, according to LeChatelier's principle, has to offset that excess and convert the oxygen to formaldehyde. And so in the course of oxygen going back to equilibrium, that oxygen will decrease. The oxygen concentration, the partial pressure is going to decrease, as well as the other reactant. The other reactant will be consumed, so the moles will go down. the product will go up because that's being produced, the moles will go up. If it's an aqueous or a gas, then the concentration will go proportionally, okay? But if it's a solid or a liquid, there is no change, because for a solid and a liquid, even if it shifts, concentration doesn't change. So that's what you're looking at in these problems right here, okay? So this is a good problem to review for your exam. If you're in my lecture, exam's not this weekend, it's the following week, okay? But look at the moles of methane, carbon, oxygen, and formaldehyde. The moles is not molarity. The moles is the individual particles. Now, for a solid, the moles can go up, but for a solid, the molarity does not change. Why? Because when the amount of chemical for a solid goes up, the volume also changes proportionally. So concentration doesn't change even though the moles increase or decrease. Please keep that in mind. There's a difference between moles and molarity. And then over here, this second column here is concentration, that's molarity. Your answer on these is going to depend on this first column, whether the reaction's moving more towards the product or more towards the reactant. You're going to base your answers on that, okay? If it's moving more towards product, of course, the concentration of the aqueous or gas will go up. The moles will certainly go up. If it's moving more towards product, the reactant moles will go down. Certainly concentrations, if it's gas or aqueous, will go down because it's going to get consumed. Now, how do you answer delta H? Delta H simply is whether heat is released or heat is absorbed. So you need to figure out whether in this reaction, this is an exothermic or endothermic. If it's, for example, let's say that this is an endothermic reaction. I'm not saying it is, but let's say it's an endothermic reaction, which means energy is in the reactant side. Energy needs to be fed into that reaction for that reaction to go. That's what endothermic means. If the reaction is shifting to the right and it's endothermic, then you treat the energy as a reactant. It's going to get consumed. The energy will drop, the temperature will drop, okay, because it's going to get consumed. If, however, the reaction is moving towards the reactant side, because energy is in the reactant side, if it's moving in that direction, then the energy will go up, it's being produced, and the temperature will go up as well, because we measure energy or heat in terms of temperature change. So that's what I want to say about this particular problem. This particular problem, the best way to solve this particular problem, H, is via the mass action expression. Write the mass action expression for this and assume that the concentration for all of them are 1, and then double it and see what happens to the Q, the mass action expression value when you double it. Does it go up or does it go down relative to K equilibrium? That's the best way to approach that. This problem right here, okay, you've got PCl5 going to PCl3 and Cl2. A lot of students have a difficult time grasping that reaction. How can you have 1 going to 2? Okay, you have 1 going into 2 because the 1 is breaking up into two species. Okay, so the problem is at 265, and that's the temperature, and it says 55% of the original PCl5 is decomposed according to the above reaction. 55%, that means out of 100 molecules, 55 will go to PCl3, 55 will go to Cl2, and 45 stays as PCl5. That's what 55% decomposition means, okay? Now, if you understand that, if you've got 1.1 moles, okay, moles again represents individual pieces, 55% of that will go to PCl3, 55% of that will go to Cl2, and 45% will stay as PCl5. Okay, you're in a 1 liter, so take the moles and divide it by the 1 liter, and you have now the concentration at equilibrium. That's what the problem says. At 265, 55% of the original PCl5 is decomposed according to the reaction, which means that at equilibrium, 55% converts over to PCl3 and Cl2. Okay, you don't have to think about the change, just know what you have in the beginning, 1.1, and what you have at the end, 55%. Once you have that and you have the concentration at equilibrium, then you can calculate the mass action, the equilibrium constant. Okay, you can calculate the equilibrium constant. The third one here, you've got iodine and hydrogen goes to 2Hi. The equilibrium constant for this is 0.17. It's a small number, but not that small. It's not like 10 to the minus 5 or 10 to the minus 8. Okay. What concentration of iodine will be at equilibrium with 0.040 molar and Hi at 0.150 molar? This is the most difficult thing that I see in terms of beginning chemistry students, at least students taking Chem 201. You're given a condition for a problem. You need to be able to interpret the meaning of what that condition is. Okay. In this particular problem, the concentration of H2 and the concentration of Hi, is that the initial condition or is that the equilibrium condition? If it's the initial condition, then you need an ice table. You need to show that the initial changes and then what is it at equilibrium. If it's the equilibrium condition, then fine, you can just stick that into the mass action expression and then solve the problem. So it takes practice to figure out what the problem presents. Is that condition that's presented in the problem at equilibrium, or is that the initial condition? Okay, because if you don't have that clear in your mind, more times than not, you're going to get the problem incorrect because you don't know where you're starting. Okay, so clue in keywords like will be in equilibrium with H2 at 0.04. Okay, you need to key in at keywords because those keywords will tell you whether or not you're at the initial or at equilibrium. That's the key. It just takes practice. So that problem is actually pretty easy. The fourth problem here, the value of Kc, that's an equilibrium constant with molarity, is 2.2 times 10 minus 10. For the equilibrium of the decomposition of phosgene, COCl2 to carbon monoxide and chlorine. If the concentration of Cl2 at equilibrium is 4.8 times 10 to minus 6, what are the equilibrium concentrations of the other two substances? Remember that phosgene is one chemical. It breaks down to carbon monoxide and chlorine. So the amount of carbon monoxide is equal to the amount of chlorine because they both come from the original species. If you know the concentration of chlorine at equilibrium, you certainly know the concentration of CO. Okay, so that's what I'm trying to tell you here. Okay, now you need to calculate the concentration of carbon monoxide, the concentration of phosgene, and then if you have the equilibrium conditions and you know what X is how much of the chemical decomposes, you can actually calculate the original concentration of phosgene. Okay, so this one's a little bit of a math problem, but it's if you set up the ice table, you should be able to come up with this answer. Okay, you're given the equilibrium concentration of chlorine. You should certainly calculate the concentration of carbon monoxide and phosgene at equilibrium. Then using the ice table, you can back calculate the initial concentration of phosgene. Okay, the initial concentration of phosgene. So let's move on to the second page. This second page is solubility. We've started talking about this in lecture. This is a solid going into its ions. The solubility S, which is the solubility, how much of it? It's like X in equilibrium. But we use S instead of X because S represents the amount that dissolves. S of calcium carbonate at 25 degrees is 6.9 times 10 minus 5. That's how much of the calcium carbonate goes into solution. 6.9 times 10 minus 5 molar. The reaction is calcium carbonate goes to calcium and carbonate. What is the concentration of calcium and carbonate at equilibrium? Okay, remember that the calcium carbonate breaks up to equal amounts of calcium and carbonate in this reaction. So you know what the solubility is, okay? That's how much of the calcium carbonate goes into solution. The amount that goes into solution is equal to the calcium concentration as well as the carbonate concentration because they're equal amount. It's a 1-to-1 ratio. Calculate the equilibrium constant for this dissolution. If you are able to write the mass action expression, the KSP equation for this, you can easily calculate the KSP. Okay. Look at this next problem right here. This is an acid-base problem, but the reason why I introduce acid-base, even though we're at equilibrium, is to illustrate to you that acid-base chemistry, at least for weak acids and weak bases, is nothing more than equilibrium. So it's going to benefit you a lot to understand equilibrium really well. Why? Because those concepts are the same concepts you use in acid-base chemistry, as illustrated by this problem. So if you think of hypochlorous acid, HClO, as just another chemical breaking up, okay, like a KSP, and that this is called a Ka, means it's an equilibrium constant for an acid. You treat Ka as K equilibrium, Kc, Kp, Ksp, it just depends on the mass action expression, then this problem should not be intimidating at all. This problem shows that you got hypochlorous acid breaking out to hydrogen and chlorous ion, okay? Those are the two. So this is, notice that they're all aqueous. So the mass action expression for this is hydrogen times chlorous ion all over hypochlorous acid. So that's the mass action expression. It's products over reactant because all of these are aqueous. You got the concentration at equilibrium. See where this word right here was found to have. When it was found to have, you've already reached equilibrium. Words like that are going to tell you where that concentration belongs, whether it's initial or whether it's at equilibrium. So it takes practice again. It was found to have 1.1 times 10 minus 4 molar. So when this thing breaks, it produces 1.1 times 10 minus 4 molar hydrogen ion. Guess what? How much of the ClO minus do you think is also formed? Because they come from the same original chemical, they should form at equal amounts. That's why the problem doesn't give you that, because you should be able to know that based on the chemistry. Okay? For every one H plus that forms, you also form its missing partner, ClO minus. So that's what we have here. Calculate the, and then 0.40 molar is the initial concentration. That's the acid you have. Then you're able to, when that's the initial concentration of acid you have, then you're able to analyze and find out that the hydrogen ion concentration is 1.1. So this 1.1 times 10 minus 4 molar. So this actually is an ice table. You know your initial. In your initial line, there is neither H plus or ClO minus at the beginning of the reaction. Then you have your change, minus X plus X plus X, and then your equilibrium. And it tells you right here what the equilibrium concentration of your H plus is. From that, you should be able to calculate the equilibrium constant. You should be able to calculate the equilibrium constant, Ka, in this case, and then calculate the ratio of the change. That would be X. Delta ClO minus is the X. That's how much is being converted over to hydrogen ion. Okay, that's the X over the initial. So if you know what the initial is from your ice table, you can calculate this ratio. This ratio you will find out in acid-base chemistry is called the ionization the percent ionization. How much of the original actually goes into, breaks apart, ionizes. Okay, so I'm sort of seeding some of the concepts in acid-base chemistry here. But again, to illustrate to you that acid-base chemistry, at least for weak acids, weak base, is nothing more than equilibrium. Okay. Number 7 here, you've got bromine going to Br atoms. These are atoms, not ions, because it's neutral on the left, it's neutral on the right. Okay, so it's not ions, it's 2Br atoms. Kc is 1.04 times 10 to the minus 3. So write the mass action expression. They're both gas, so they're both going to be represented in the mass action expression. Okay, then what you want to do, well, before you write the mass action expression, you want to write your ice table. 0.2 molar vessel contains an equilibrium mixture of 0.245 Br2. Okay, what is the mass of Br in the vessel? So it says right here, a 0.20 liter vessel contains an equilibrium mixture of gases. Of the gas has 0.245 grams of Br2. You don't know what Br is, but you know what Br2 is at equilibrium. Okay. Of course, whenever you're dealing with any mass action expression, then you need to either deal with the partial pressure or the molarity. In this case, you have the volume, you've got the mass, you could easily work with molarity in this particular case. Plus, they give you the Kc. They didn't give you the Kp. Probably easier to work with molarity for this problem. Once you set up the ice table and set up your mass action expression, you can back calculate the moles of Br. And if you know the moles of Br in this volume, you can calculate the mass of Br. Okay, so it's a little bit, it's mostly general chemistry in making sure you guys know how to do your conversion. What is the total pressure in the reaction vessel at equilibrium? Remember, the total pressure is the partial pressure Br2 plus the partial pressure Br. If you know the moles and you know the volume, then you know PV equals nRT. You can use PV equals nRT to calculate the partial pressure of Br2 and Br in this reaction to get the total pressure. So this one just requires you to use PV equals nRT, the second problem, number 8. Okay. Finally, in the last problem, what we have here is carbon dioxide and hydrogen goes to carbon monoxide and water. Okay, I actually give you the equilibrium concentration of carbon dioxide, hydrogen, water, and CO. These are it right here. You should be able to calculate Kc. You should be able to calculate Kp. Those are pretty straightforward. What are the concentrations of the 4 substances in mole fraction? So this goes back to activity 1. Are you guys able to take molarity and calculate mole fraction? Remember, mole fraction is the moles of that individual component divided by the total moles of the mixture. In this particular case, the mixture is CO2, H2, CO, and water. That's the mixture. This is not just a chemical in water anymore. It's actually one chemical in a combination of 3 others. So the mole fraction is the moles of that substance in the total moles in that mixture. So you calculate the mole fraction for each, and then instead of molarity in the mass action expression, substitute the mole fraction concentration and see whether or not the mass action expression expressed in mole fraction is equal to Kc. That's the only thing that's being asked here. Okay. So instead of equilibrium constant in terms of molarity, Kc, you're going to use equilibrium constants in terms of mole fraction. And what is the lesson there? The lesson there is to see whether or not you can get away with using mole fraction or any type of concentration for the mass action expression other than molarity. Sure. Okay. So today will be a brief lab. discussion. I just want to show you where to put your answers for the activity 6. And it's good that we have activity 6 now, because in lecture, at least, we just finish up equilibrium. So you guys have all the ammunition to answer these questions. Well, but today, what I want to do is just kind of show you the similarities between the lab manual questions and where you would put that in Canvas. We do this because when we get too much papers, we get behind, which is what I'm beginning to be doing. I'm finishing up grading your reports, and I hope to be done by this weekend. So you guys should have an idea of how you're doing in the reports that you submitted. So just be a little bit patient with me, and I promise I'll get that to you by the weekend. But for this activity, we do have it in Canvas. That way it can be self-graded, and then all the instructors, this is true for all Chem 201 instructors, what we need to do is go back and verify your work and correct any mistakes Canvas has done in terms of understanding what you write down in the answer sheet. So I'm sharing my screen with you so you can see exactly where to find this. Of course, it's going to be under module. Okay. And under module, you guys are going to go right here after the equilibrium. And you can certainly watch the PowerPoint. What I will also do is I will take the Zoom session from last time and edit it and then upload it probably tonight or tomorrow, so you guys can see that. But this is it right here. It's a 10-point activity. You click on that, and this is how you would see it as a student. I have next to it the lab manual version. And what you want to do always when you have these things is double check that the numbers are the same. Because what we will do from time to time is that we'll take the Canvas version and change the values. And that way we understand that students just share their work. And sometimes they share their work and the person who they share it with just puts the answers without thinking. So to keep you guys honest, we adjust the numbers at times. So let's just take a look. This was just been up for about a semester or two. So probably we haven't changed the numbers, but you never want to leave it at that. Okay. So when you open this up, what you would see is the questions corresponding to the questions in the activity. The first one's an equilibrium, and this is a good practice because it will allow you to practice LeChatelier's principle in terms of the figuring out whether the reaction shifts to the left or to the right. We talked about this last time, and what happens to the moles and the concentration. So here, you need to balance the equation first. And if you have a small screen, you're at a disadvantage because you don't see the whole question the way it's intended. So if I stretch my screen here, you can see that it's a better layout. The other thing you can do if you have a small screen is try and do control minus. When you do control minus, you make the size of the font and the screen smaller, so it might fit. You do control plus or command, okay? Then the font becomes bigger and then everything squish. But if you do command, that's the practice if you have a PC, okay? Then you can see that everything can fit. Or you can always stretch your window if you have a big screen. Or if it's like this, what you can do as well is you can actually, there should be a scroll bar in the bottom that you can scroll left to right. Sometimes that happens. Let's see if I can't get that. Okay. I guess not under student view. That's why I have student view, so that you can see that if you don't see anything like this right here, all you see is like right here, you see it's cut off, and you might think that you don't have access to it, so you don't answer that question, there is a scroll right here so that you can reach that. My suggestion to you is to answer the questions first in the lab manual. You're going to have to take a picture anyway, so you might as well put it there, and then transfer that answer onto Canvas, provided the questions are the same. So let's just do that. So the first question is the equilibrium between methane, carbon, oxygen to form formaldehyde. And you can see that's the, let me stretch this. That's the equation right here. It gives you a delta H of negative 135.2. And in the regular paper, it's also 135.2. So these questions seems to match. The first set, you can just do a drop-down menu, no change, left or right. Those are it. And so if you take time to answer these questions here, make sure you don't just lethargically select the question here, because sometimes what I find out is that you become lethargic in answering these questions and it doesn't match what you have in your paper, and then it's going to be counted wrong, because the one in Canvas is the one that we grade. Okay, so please make sure that you take time and make sure they're the same. Here, we're looking at the moles, and here you're also doing the moles. So you're just transferring your answer from the lab to Canvas. And again, it's a drop-down menu. No change, decrease, increase. And those are the only three choices. Don't make up something like it changes to 0.56. That's not the question. It's just figuring out whether the reaction shifting left or to the right, or nothing's happening. So these questions right here, this is the molarity. And then that's it. Okay, you don't have to upload your answer for that question. The next question is this right here, PCl5. And so it tells you right here, 265, 55% of the original PCl5 decomposed. And that pretty much matches this first statement. And it tells you that you have 1.1 moles of PCl5. So if you put your answers here in the lab manual, then you can also transfer it here. And then it asks you to calculate the equilibrium constant for that reaction. So you can transfer it again. And here, you're going to have to upload your work, take a snapshot of that section, and then upload your work here. Okay. Then the second question, or the third question here, is the hydrogen iodide. This has an equilibrium of 0.170 at 500. This also is 0.170 at 500. The concentration of HI is 0.150. Concentration of HI is 0.150. So these questions are identical. Just take your answer from the worksheet and transfer it here. And that's pretty much what you do for the rest of these. Again, I remind you that sometimes actually, other than the first question, everything should fit in your screen if you make the font small. If the font is big, of course, then what happens is you get to the point where everything, you're not going to see the entire question. So again, Command minus or Command plus will allow you to adjust the screen on Canvas so that it fits in your monitor. And it looks like that pretty much is what Canvas is, and that's the way it's going to be for the entire semester for Chem 201, is that you guys will have the lab manual to work with, and then you're going to put your answer in Canvas and take snapshots of certain questions to upload. But always, I remind you, double check to make sure that the numbers in Canvas matches the one in your lab manual. Otherwise, you'll be doing a problem in the lab manual. You transfer that into Canvas and it'll be graded wrong. I think in this case, everything should match. But again, to keep you guys honest, we do change it. The principles and the strategy to solve the problems are identical.